Hi everybody. Today I am going to discuss about our systems course project called Real-Time Sentiment Analysis on YELP Dataset. I am Abhishek and my other teammates are Sandeep, Akshay and Anvita. Now coming to the project description. So the main objective of this project is to build an efficient end-to-end pipeline for real-time movie rating predictions and then analyzing the latency and accuracy. So the methodology involved here is first we pre-process the data using PySpark, then use PySpark ML libraries to train machine learning models, then finally use Kafka for real-time processing. So the dataset used here is YELP dataset, which is a movie review user movie rating dataset. Now coming to the overall architecture or design of this particular project. It has two major components. One is Kafka producer and the other one is Kafka consumer part. So for the coming to the producer part, so we take a small subset of YELP dataset and we can basically send mm, each record using console or code to a Kafka topic whose replication factor was 3. 3 is an arbitrary number over here which is just greater than 1 just to ensure fault tolerance. And now the Kafka consumer basically it's subscribed to the particular topic in which Kafka producer sends the messages to. And and in Kafka consumer what happens is like it loops through each of the message in the Kafka topic and then it processes the input to the model by loading the pipeline which was saved from the pre-trained model, and then it also loads the machine learning model which was trained on YELP dataset and use it to predict movie rating. And then finally we display the movie rating in a console and we log the results in a log file or warnings as well into a log file.
This slide shows the data analysis we have performed in this project. Um, uh, as you can see, here is a snapshot of the top 5 rows in our training data. In a training data set, the text reviews serve as the input feature, while the star ratings assigned to the movies constitute the output feature. Additionally, we've also incorporated temporal information through the date feature, indicating when each review was posted. The features funny and useful are also utilized, with funny taking a value of 1 if the review is considered humorous and 0 otherwise, and useful capturing similar sentiments. Below is the data frame schema which we have used in this project. The PySpark data frame adheres to the following data schema as illustrated in this snapshot. Further data analysis we have performed in this project is indicated in this slide. As it's evident in the initial graph, the average text length is 100. However, the histogram also reveals the presence of infrequent but notably long and lengthy reviews. To streamline a model and enhance computational efficiency, we have constrained the analysis to reviews with text lengths up to 1000. This opting for this shorter text also translates to quicker computations, thereby reducing the latency. Hence, we have constrained our analysis to reviews with text lengths up to 1000. The chart on the right illustrates the distribution of ratings in the YELP dataset utilized for our project. Here, the output consists of rating stars ranging from 1 to 5. This also reveals a very imbalanced dataset. This imbalance is particularly evident with the 5-star rating class, which is the predominant category, while the 2-star class represents a minority. Um, we have to keep in mind and recognize the potential introduction of bias into our machine learning model here, especially with the underrepresented 2-star class. It's also imperative to be mindful of this imbalance during a model training. Hence, we've carefully selected the models to mitigate its impact and ensured thoughtful consideration throughout the training process.
Hi, this is Sandeep. I'll be discussing about pre-processing and model training. First, pre-processing the data. So we have loaded our data into PySpark data frame, which uses Spark plus SQL internally. Second, we divide our dataset into train and test data in a ratio of 70:30. Third is the feature engineering layer, which uses the Spark ML library. For example, we have considered tokenizer, which converts the text into sequence of words. Second, we have used a stop word remover, which removes the unnecessary words like I, a, and. Third, we have used count vectorizer and inverse document frequency, which converts the text data into meaningful numbers. Now, when it comes to the modeling part, we have trained multiple models and saved the checkpoints. So this is very helpful during our inference at Kafka consumer. So we have used the concept of checkpointing to avoid the recomputation. We have mainly trained two models. One is naive-Bayes model and multinomial regression. Now let's discuss about model performance and test results. So we have tested our models on 2.4 million samples, which is 30% of the total data. Now, naive Bayes has been outperformed when compared to multinomial regression. Naive Bayes has a close accuracy of 70%, but multinomial has an accuracy of 61.6%. Now, when it comes to the system's performance, we can see that latency it has taken for 24 records is around 28 seconds. That means on average 1.2 seconds per record. Now, to ensure the end-to-end pipeline error-free, we have sent sample records to Kafka topic and processed them using Kafka consumer, so which ensures the pipeline is working as expected. On top of it, we have also performed unit tests on few utility functions like length UDF to ensure its proper functionality. Now let's discuss about the possible improvements. So we have after Kafka consumer, we are storing the predictions on a log file. But on top of it, what we can do is we can use tools like Grafana, which can further utilize these log files and create meaningful information during real-time processing. Second is the model update. Currently, we are using a static model, ML model. Instead of that, once more data arrives in the future, the model can be trained dynamically and this can be integrated with the Kafka consumer. Third is the schema management. For example, tools like Apache Avro, which has centralized schema management. So in this way, producer and consumer can retrieve the schema as needed. So all this can be a possible improvements for our project.
Hi, this is Akshay. I'll be discussing about analysis, experimental results, and goals. Let's now dive into the analysis and experimental results. So here we have actually considered total of 16,000 samples, and then we have tried to fit the naive Bayes as well as multinomial regression model on the 16,000 samples using different number of CPU cores. So we have tried 1, 2, 3, and 4 CPU cores. So this was the output times we were able to notice. So here we can see that going from 1 to 3 cores in both the cases, the CPU time taken for the operations fitting the model have got reduced, and from 3 to 4 it increased a little. So basically we can notice that the reduction in this time is because there is some parallelism and concurrency being occurring in the model. So as we are increasing the number of cores, these cores are basically sharing the work and computation. That is the reason here we can see parallelism, whereas from 3 to 4 we can see a slight increase in the time. This is because like as the number of cores increased, the overhead times for communication and passing messages between these cores increases. So that is the reason like this is slight increase in time from 3 to 4. Now next, going into the profiler results. So here actually we have tried to fit the naive Bayes model using the PySpark profiler, and we were able to produce these results. So here we can see that like this is the CPU time, total CPU time, as well as the percentage of time utilized by that particular operation. So these were the operations in the naive Bayes model.fit. So as you can see, these were just basically the top k operations. You can see that like most of the operations here are related to communication. So basically notifying the thread, mm, getting messages from the stack, thread stack, conditional wait, so basically acquiring lock and waiting for the resources. So here we can see that like most of these are basically the communication related messages. So the majority of overhead is basically because of this communication related messages itself. So now coming to the goals. So coming to the milestone goals, first of all, we have shown you different analysis we have done on our dataset. Thereafter, we have also done the pre-processing on our data. Basically, we have done the tokenization, we have done TF-IDF and count vectorizer, etc. Later on, we have trained the two types of models, multinomial logistic regression as well as naive Bayes, and compared these results. Later, we have also set up the Kafka pipeline and deployed the model on Kafka, which we will be seeing in demo shortly. So coming to the final project goals, so we were able to build an efficient end-to-end pipeline for real-time predictions. So we were also able to analyze latency and accuracy. So let's now get into the demo.